Alright, Honors Chemistry. This is Lesson 17 on gas stoichiometry. Alright, so we're moving through stoichiometry. We spent a good deal of time on that first arrow there, that first column of pure substances where we convert from grams to moles. And we do that using the molar mass. 1 mole equals a certain number of grams depending on the substance. And the substance could either be in gas form, as long as it was a pure substance, or liquid or solid. And from converting from grams to moles, then you can use the chemical equation in moles. Now we're going to focus on the middle column, and that's if we're dealing with an unknown gas, possibly. But what we're going to do in this case is you can convert from if you know the pressure, temperature, and volume of the gas, you can calculate the number of moles. And using that number, you can then put that into the chemical equation to use the chemical equation. You can then obtain some number of moles from the chemical equation and come back out and figure out either pressure, temperature, or volume of the gas. We're going to really stick to a basic concept here of standard temperature pressure, which I'll deal with. That makes the problems easier, and we'll deal with that at this point. So the relationships of Boyle's, Gay-Lussac's, and Charles' laws are as follows. Boyle's law is that the pressure P1 V1 equals P2 V2. What the P1 V1 means, or what the 1 means, is before you've made the change, and the P2 V2 means after you've made the change. So the pressure times the volume before you've changed one of those variables equals the pressure volume after you've changed those variables. So essentially Boyle's law relates pressure and volume. Gay-Lussac's law relates temperature and pressure. T1 P1 equals T2 P2. And Charles' law is temperature and volume. It relates those two. Those can be combined into something called the combined gas law, and that basically puts them all together. So P1 times V1 divided by T1 equals P2 times V2 over T2. I'm not giving you any numeric problems with these because what we're kind of doing is moving past these to the ideal gas law. These were all used to derive the ideal gas law, which not only includes pressure, temperature, and volume, but also number of moles. And so we're kind of moving straight into that in a little more direct path to getting where we want to go and learning about gas laws. So as we move further into the course, unit of measurement cancellation will become more complicated. Use the principles of fraction division to cancel units. In other words, if you have a fraction over a fraction, fraction divided by a fraction, you flip the bottom fraction and then multiply, something you learned in math class some years ago, I think. So if two levels of the fraction have a common word, then the units on those levels can be canceled. So on the top fraction, up in the numerator, you have numerator top, numerator bottom. On the bottom fraction, you have denominator top and denominator bottom. So anything in numerator top can be canceled with anything in numerator bottom because they have the word numerator in common. Also, anything in numerator top, it should be the same unit. So anything numerator top, such as grams, let's say we're talking about grams, could be canceled with grams in either numerator bottom or denominator top because they both have the word top in common. So we've talked about this a bit in class. So let's go ahead and do an example. So there you have a whole bunch of just random units I threw together just for the sake of practicing this. So we start with the Kelvin and the Kelvin. Those are in numerator top and numerator bottom, so they have the word numerator in common, so they can cancel. Atmosphere and atmosphere. So one of them is in numerator top, the other is in denominator top. They both have the word top in common, so they can cancel. Liters and liters. One of them is numerator top, the other is in denominator top. They both have the word top in common, so they cancel. Down near the bottom, you have grams and grams. You have grams in denominator top and grams in denominator bottom. They both have the word denominator in common, so they cancel. You could have also canceled the grams in denominator bottom with the grams in numerator bottom, since they both have the word bottom in common. We didn't do that, but you're going to end up with the same answer either way. Doesn't matter what path you take as long as you do the cancellations properly. We have moles in numerator bottom and moles in denominator bottom. They both have the word bottom in common, so you can cancel those. And that's everything. So the only thing we now have left are liters and grams. Now again, that bottom ratio, liters is denominator bottom. So you treat it like you're dividing two fractions. You flip the bottom and you multiply. That means that liter, that L in the very bottom, in denominator bottom, is going to flip and go all the way up to the top because you're going to flip that bottom fraction. And so what you end up with is liter on the top and gram on the bottom. Okay. Standard temperature and pressure is a temperature of 0 degrees centigrade, which is 273 degrees Kelvin, and 1 atmosphere of pressure. 0 degrees centigrade, 273 Kelvin, is the freezing point of water. And while that might sound cold to typical gas molecule like H2 or O2 or N2, that's not cold at all. It's those require hundreds of degrees below 0 centigrade in order for those to start to freeze or become liquids or solids. So 0 degrees centigrade for a gas molecule is not really all that cold. Using STP, standard temperature pressure, and the ideal gas law, we can determine a relationship between the number of moles and the volume of the gas. We can determine 1 mole of gas is equal to 22.4 liters. So we're going to go ahead and take PV equals nRT. We're going to solve it for volume, dividing both sides by P. And now you plug in 1 mole. So we want to know what the volume is of 1 mole. There's the gas constant with the units liter atmospheres over mole Kelvin. Times temperature is 273 Kelvin. It has to be in Kelvin. And the pressure is 1 atmosphere. So that's standard temperature and pressure. 1 atmosphere, 273 Kelvin. Now check your unit cancellation. Kelvin. So you have, when something is only on one level, that means it's on the top. So you have 273 Kelvin is in the numerator top, and the other Kelvin is in the numerator bottom. So Kelvin numerator top cancels with Kelvin numerator bottom. Moles. You have moles in the numerator top and moles in the numerator bottom, so they cancel. Atmospheres. You had atmospheres in the numerator top and in the denominator top, so they both have the word top in common, so they will cancel. That means the only thing you have left is liters for your final unit, which is what you want because you're looking for volume. So that's how the gas constant makes all the units cancel except for the one that you want to have in your final answer. And if you multiply those numbers, 1 times 0.0821 times 273 divided by 1, it gives you 22.4 liters. So 1 mole of any gas, it doesn't matter what gas you're dealing with, at standard temperature and pressure is going to equal 22.4 liters. So that's what it says there. Okay, let's do a problem. How many grams of water, H2O, will be produced from the combustion of 12.4 liters of CH4 at STP? All right, so this looks kind of busy down there, and I did ask you to draw this on your assignments. So there you have the chemical equation in the dashed line, and inside the dashed line is moles. So chemical equations only understand moles. That's what all the numbers inside of a chemical equation represent, are a number of moles. Okay, up above, we're dealing with gases. So we're talking about liters. That's our world is liters when we're dealing with gases. And we just said that if they're at standard temperature pressure, and the question says that, STP, so it is standard temperature and pressure, the relationship between moles and liters is always going to be the same. 1 mole equals 22.4 liters. And that's true, so you'll notice that's for all of the conversions, moles to liters there up above the dashed line. Now we go down to the bottom, and it's exactly what we dealt with prior to the break and for some weeks now. You have molar masses of each of the substances there. You know how to figure those. If you don't, come see me during tutoring and we'll work on that. And then down on the very bottom set of boxes, it's the number, it's the grams, it's the amount in grams. Okay, so let's go ahead. So we want to know, we're starting with 12.4 liters of CH4. So the 12.4 goes in the liters box up at the top, up above CH4. And our question mark, how many grams of H2O, goes in the bottom right box. It's down at the very bottom, way over on the right. It's in the grams row, and it's under H2O. So now you have to find a path to get from 12.4 to the question mark. So the first step is to go from 12.4 liters through that standard conversion for liters to moles. 1 mole equals 22.4, and that will get you the number of moles of CH4 that you have. Now you can only move sideways when you're inside the chemical equation, so this is a moles to moles conversion. Moles of one substance to moles of another substance. So it goes across like that, from moles of CH4 to moles of H2O. That's the second conversion. And now you're ready to come out for your final answer, which is grams of H2O. So you're going from moles of H2O, and you're coming down to grams of H2O, and you're using the molar mass of water. 18.02 grams equals 1 mole to do that conversion. So it's a 3-step problem. So up above, we go ahead and we write down what we start with way over on the left, 12.4 liters of CH4, and what we want to end with at the end of the problem, and that's some number of grams of H2O. And we see it's 3 conversions, so it's going to be 3 boxes. I don't draw the boxes in this particular problem, but you can do them if you want. Okay, so the first conversion is going to be the 1 mole equals 22.4 liters right there to get us from liters of CH4 to moles of CH4. So you're going to use one of those 2 conversions. Think about which one it would be. Since you have liters of CH4 that has to cancel out because it doesn't appear in the final answer, liters of CH4, then that means it has to go on the bottom of the conversion. So that's going to be the first one. So you go ahead and write that there. So liters of CH4 cancels with liters of CH4. So again, that's always this pattern. Just kind of get used to how that pattern works, and which one goes on the bottom. Okay, so now that puts us in the box moles of CH4 inside the chemical equation. You don't have to do that calculation, but it would be 0.554 moles of CH4. Now we go to the next conversion. That's to get us sideways from moles of CH4 over to moles of H2O. And all you do is take the 1 CH4 and the 2 H2O and put an equal sign between them, but don't forget to add the word moles. So up above, so what we have is 1 mole CH4 equals 2 moles of H2O. You don't care about O2 or CO2 in this part. So you make a ratio out of those two. 1 mole CH4 over 2 moles of H2O, or 2 moles of H2O over 1 mole of CH4. So which one goes on the bottom of that second conversion? You've got to get moles of CH4 to cancel out since it doesn't appear in the final answer. So you're going to put this one up there, and that way moles of CH4 cancels with moles of CH4. Now we're sitting over in the moles of H2O box. So it's 1.11 moles of H2O. You see that appeared in the box over on the right. So that's where we are right now. Again, you don't have to do that calculation directly. Now we're going to get from moles of H2O out to grams of H2O. That's what we're interested in for our final answer. So we're going to use the molar mass conversion for water. 1 mole equals 18.02 grams. So you make the 2 ratios out of that. Which one is going to go in the third conversion? Which one do you need to cancel out? You need moles of H2O to cancel out. So moles of H2O cancels with moles of H2O. And the only thing left is the grams of H2O, which is what you want for your final answer. So that's how you know that you set the problem up properly. So now you simply multiply everything. 12.4, everything on the top. 12.4 times 1 times 2 times 18.02 divided by everything on the bottom. Divided by 22.4, divided by 1, divided by 1. And that gives us 20.0 grams of H2O. And that's your answer. If you want, you can write it in the box down below, but you don't need to do that on your assignment. Okay, so I would study this problem over and over, or any of the other ones on Lesson 12, on the Lesson 12 video. Really nail down this concept of how you do these problems. I mean, you might have to watch them 4, 5, 6 times if you're still having trouble with this. And if you are, do that, and then come talk to me in tutoring. And let's walk through some of these together, okay? This is not impossible to understand, but it is tricky. It's like something you've never done before. Okay, now we're going to go on to one that is... Okay, so here's our next problem. How many grams of H2O will be created from 28.7 liters of CH4 at 1.06 atmosphere and 290 Kelvin? So you can see that this is not standard temperature and pressure. Standard temperature is 273 Kelvin and standard pressure is 1 atmosphere. So this is not standard temperature pressure. So we're going to have to calculate the number of moles using PV equals nRT. So the conditions are not STP. For this problem, we can compute the number of moles using PV equals nRT. We solve for moles, N. So there's the equation. And if you divide both sides by RT, you get N equals PV over RT. Now you can go ahead and plug in the numbers. First, check to be sure that the units of measure are what they need to be for the ideal gas law. So volume is in liters, pressure is in atmospheres, temperatures in Kelvin, so everything's good as far as the units of measure go. So there it is. That's all the numbers plugged in. So go ahead and use your rules for unit cancellation to see that you come up with the proper units of measure. So atmosphere in the numerator top, remember if there's only one level in the numerator, then it's on the top. So atmosphere in numerator top and atmosphere in denominator top, they have the word top in common, so they cancel. Kelvin in denominator top and in denominator bottom, they both have the word denominator in common, so they cancel. Liters is in numerator top and in denominator top, they both have the word top in common, so they cancel. And that leaves us only with mole. Now, since mole is on the very bottom, it's in the denominator bottom. Remember, for a fraction, you flip the bottom and multiply. So by flipping the bottom, that flips moles all the way from the bottom all the way up to the numerator top. And that's your final unit of measure. And if you crunch the numbers there, multiply 1.06 times 28.7 divided by 0.0821 divided by 290, that gives you 1.28 moles. So you would have that many moles of any gas, it doesn't just have to be CH4, of any gas at those conditions of temperature, pressure, and volume, you would have that many moles of any gas. Now we can go ahead and work the problem. We want to know how many grams of H2O we're going to get. So there's the equation that we just did on the previous slide. Since we're not dealing with STP, you don't see the 1 mole equals 22.4 liters anymore because it doesn't apply to this problem. That's only if it's at STP. This is not. So we had to do a custom calculation here to come up with the number of moles. So that number, 1.28 moles of CH4, you can go ahead, since it's in moles, go ahead and put it right into the chemical equation right away. And there it goes, right under CH4. The rest of the problem now is like the last one. From that point, you're going to go across the chemical equation from 1 mole of CH4 to 2 moles of H2Os. So you're going to compute the number of moles of H2O. And then from there, you're going to go through the molar mass for water. 1 mole equals 18.02 grams to get the number of grams of water. And there's the question mark down there. So again, it's a 3 conversion problem. So the first one we've already done. So we've got the 1.28 moles. Now this is the same set of conversions we had in the last problem. There's 1 mole of CH4 for every 2 moles of H2O, or 2 moles of H2O for every 1 mole of CH4. Which one goes in? Which of those two do you use? Well, you see moles of CH4 up there in the big red box, so you need to get that to cancel because it doesn't appear in the final answer. So we're going to go ahead and use this one. So 2 moles of H2O over 1 mole of CH4, that makes moles of CH4 cancel like that. Now the last conversion is going to be the molar mass of water. Oh, I went ahead and computed, so it's 2.56 moles of H2O. In other words, the chemical equation tells us we're going to get twice as many moles of water, H2O, as we started with moles of CH4. It's a 2-to-1 relationship. So if we had 1.28 moles of CH4, you double that number to get the moles of water, 2.56. Now we're going to come down through molar mass of water. Okay, which one of those two are you going to choose? You're going to choose 1 mole of H2O, and that's going to make moles of H2O cancel. Your last man standing is grams of H2O. So now you can go ahead and do the calculations. 1.28 times 2 times 18.02 divided by 1 divided by 1, and that gives us 46.1 grams of H2O, and that's your final answer. Go ahead if you want, put that in the box, and that's that. Okay, so that's how we do these problems. All right, density. Gas density is the mass of the gas divided by the volume it occupies. Usually in physics class, when you deal with the concept of density, you may have a ball of cotton, a big ball of cotton, and a steel ball, a small steel ball that weigh the same. But the steel ball is more dense because its mass is concentrated in a smaller volume. So density is not just how heavy something is, it's how tightly packed together that mass is. So density is mass divided by volume. So in the case of gas, it's the mass of the gas divided by the volume. So there's 1 hydrogen gas molecule in the volume to the right. When a second molecule is added, the density doubles. You have twice as much mass of hydrogen in that same volume, so the density doubles. Another way we could have done it is if we had shrunk the volume down. We had kept just 1 molecule in there, but we shrunk the volume down to half the original size. That would have also created an equal density to this. So there's 2 ways you can change density. You either add mass, or you either change the mass or you change the volume. Either one of those ways can either increase or decrease density. So density can also be increased when volume is decreased. So density is equal to mass over volume. D equals M over capital V. Sometimes books use for density, sometimes they use the Greek letter. It said rho. It looks like a scripted P, but it's pronounced rho. And sometimes that's used for density, but let's just keep it simple. We're just going to use lowercase d for density. So the molar mass of a gas can be determined if its density is known. So molar mass equals density times the gas constant R times temperature in Kelvin over pressure in atmospheres. This formula can actually be derived from the ideal gas law, PV equals nRT, but I'm not going to do that. It's too much information. You don't need to know how to do that, but just understand you can get this from the ideal gas law. If you want to see how it's done, just come see me sometime. Anyway, so that's molar mass. So mm is molar mass, D is density, and it's measured in grams per liter. That's the units of measure that you need for the density. So if you're given a mass in kilograms, you need to convert to grams. If you're given a volume in milliliters, you need to convert to liters. So this formula shows that the molar mass of a gas can be determined without knowing what substance the gas is. You may remember back when we did empirical formula and molecular formulas, and we figured out the molecular formula, we needed to know the molar mass of an unknown substance, an unknown hydrocarbon. And we were asking, well, how can you do that? I said at the time, how can you do that? It's possible to do that, to know the molar mass of a substance, of a gas, without knowing what it is. In other words, you can't go to the periodic table if you don't know what it is. So you can do it, and this is how you can do it. You can figure out the molar mass of an unknown gas using this formula. Okay, Dalton's law of partial pressure states that the pressure of a mixture of different gases in a container is the sum of the individual pressures of the gases. It's a pretty simple law to understand. So the total pressure inside a container, let's say you had nitrogen molecules N2, oxygen molecules O2, and hydrogen molecules H2. If you took the pressure of each one of those separately, they would add up to the total pressure of all the gases in that container. If the gases occupy the same container at the same temperature, then the pressure is directly related to the number of moles. So if you assume that the temperature is the same and the container is a fixed container, so we said that means the volume is going to be the same whenever you hear that term rigid container or it's a fixed volume. So R, T, and V are all constant. They can't change. So the only thing that can change to affect the pressure is the number of moles. And we learned with Avogadro's law that if you double the number of moles, you'll double the pressure. If you cut the number of moles in half, you'll cut the pressure in half. So there's a direct proportional relationship. As one goes up, the other one goes up, and as one goes down, the other one goes down. So if you assume for P1, the pressure for gas 1, let's say that's nitrogen, is N1 times RT over V. P2, let's say that's oxygen, O2, equals the number of moles of oxygen, that's what N2 would be, times RT over V. RT over V is the same as in the first equation. And if we said that the third gas is hydrogen gas, H2, and again, RT over V is the same, so that would be proportional to the number of moles of hydrogen, N3. So the only thing that's going to change in any of those three is the number of moles. So the ratio of the moles of a specific gas in a container divided by the total moles of the gas is called the mole fraction. So it's designated by this kind of X-looking letter. It's called chi, but it looks like a big X, kind of scripted X. So if we want to know the mole fraction of N1, let's just say we have two gases, nitrogen and oxygen, which is what air is. And we want to know the mole fraction of N1, we simply take the fraction of, that is the number of moles of N1, divided by the total number of moles of the gases. That's assuming we only have those two gases, N1 plus N2. So N1 over N1 plus 2 will give us the fraction that is N1. There's no units to it because both the units and all that is moles. They're going to cancel out. So it's just a number. Since the partial pressure of gas P1 is proportional to its mole fraction, then if we can know the total pressure of the gas and know the mole fraction of a particular gas in that mixture, then we can figure out what the pressure of that particular gas is. It's simply proportional to what its fraction is of the total moles in the container. So example, a container holds 2 moles of O2 gas and 1 mole of H2 gas. What is the partial pressure of O2 gas if the total gas pressure is 960 torr? By the way, if you're given a pressure like this and you don't need to convert to some other unit for pressure like atmospheres, you don't do it. You just go ahead and leave the answer in torr. You only convert to atmospheres using the ideal gas law because the ideal gas constant is in atmospheres. So answer, find the mole fraction of O2 and multiply by the total pressure. So there it is. So the pressure of, we're saying that gas number 1 is the oxygen. So it's the total pressure times the fraction that is oxygen. So that's 960 torrs, the total pressure. We said that 2 of the moles were oxygen, and the total number of moles in the entire container is the 2 moles of oxygen plus the 1 mole of hydrogen. So 2 plus 1 is 3. So the fraction is going to be 2 over 3, or 2/3. 2/3 times 960 equals 640 torr. So that's how you would calculate a partial pressure. Okay, kinetic molecular theory, we're just going to touch on this. It's just some of the laws that govern how gases move and react. So number 1, gases consist of a large number of particles that are in continuous random motion. Number 2, the combined volume of all the gas particles is very small compared to the volume of the container. So in other words, most of the container is going to be empty space, which means generally speaking the molecules are not going to interfere with each other very much because they're not going to hit each other all that often. Number 3, The attractive and repulsive forces between gas particles do not exist. This is the main characteristic of a gas. Gas particles are separate from one another. So in other words, the very first slide of the last lesson, we talked about how molecules or atoms have coulombic forces that attract them to each other. So we're just going to say that those forces are so small compared to the amount of kinetic energy that they have that's keeping them apart, that effectively those attractive and repulsive forces do not exist. 4. Energy can be transferred between gas particles but does not increase or decrease. So think of it like balls. If you've ever seen a pool table and one ball strikes another, they just kind of bounce off each other and keep rolling. Well, that's kind of what's going on here. The gas particles will click off of each other, but they won't slow each other down. They may change directions, cause each of them to change directions, but they won't cause each other to slow down. Well, it's what's called in physics a perfectly elastic reaction. It's like two billiard balls or pool balls bouncing off each other, and they just keep going without losing any speed or seeming to lose any speed. 5. The average kinetic energy of the gas particles is proportional to the absolute temperature, that is the Kelvin temperature. This means that the temperature in Kelvin reflects the average kinetic energy. So if something on the Kelvin scale is 100 degrees and another gas is 200 degrees, then the 200 degree gas would have twice the average kinetic energy of the 100 degree gas. That's on the Kelvin scale, not the centigrade scale. So there you have two little particles right there. One of them is moving to the left at 10 meters per second and the other is moving to the right at 10 meters per second. You may remember from physics that the reason the negative sign is in front of one of them is that one of the directions is negative. Oftentimes we say going to the left is negative. It doesn't have to be, but we a lot of times say that's the negative direction because that's the way a number line would move, in the negative direction to the left. So the positive and negative are the same speed, but the velocity is different, one positive and one negative, because velocity has direction. You may remember that from physics. Okay, so if we took the average velocity of these two particles, it would simply be adding them together. You take an average, you add two numbers together, and then divide by the number, how many numbers you have. So 10 plus negative 10 divided by 2 gives us 0. So the average speed of those two particles is 0 meters per second. Yet that doesn't seem right, because we say, well, wait a minute, they're both moving. How can the average speed be 0? And the answer is simply that they're moving in opposite directions. One is positive, one's negative. And so velocity, average velocity, is 0. So you say, well, that's not a very good way of measuring the speed of particles in a gas, because a lot of times some of them are going to be moving one way, some of them are going to be moving the other way, and you're going to end up with something that cancels out like that, like these two seem to cancel out. So the way you use root mean squared is like this. For the root mean squared speed, we square the velocities, then take their average, and then take the square root. So you kind of do it in the reverse order of the name. You square the velocities, that's the S. You take the average, that's the mean, that's the M. And then you take the root, the square root of of what you get there, and that will give you the root mean squared value. Okay, so first we're going to square. In root mean squared, the first thing you do is square. So we're going to square 10, and we're going to square negative 10. 10 squared is 100. Negative 10 squared is also positive 100. You add those together, you get 200. Then you take the mean, that's the average, you divide by 2. So 200 divided by 2 is 100. And then finally the last step is you take the square root of 100 and you get 10 meters per second. So whereas the average velocity of those two particles was 0, the root mean square speed is 10, and that makes more sense to us. If we want to know what the speed of a typical particle is, we don't care what direction it's going in. We just want to know how fast it's going. So the root mean square computed 10 meters per second, which is really what it seems like the average speed of those two particles should be, not 0 meters per second, which is what the velocity gave us. So velocities have a directional component and cancel out. RMS values only account for the speed and not direction, and give the average speed. Okay, effusion and diffusion. So the formula for the actual speed of a gas particle in meters per second is, and this is it. So we talked about Graham's law of effusion, and what we came up with was a relative speed. We could tell how much faster the smaller particle was going than the larger particle. We knew the smaller one was going faster. You could tell us that the smaller particle, for example, was going twice as fast as the bigger particle, but it didn't tell us exactly what that number was, how many meters per second. This formula actually tells us the number in meters per second. And so the abbreviation for speed in this case is u, that small u, and it's equal to the square root of 3 times the gas constant times the temperature in Kelvin over the molar mass. So you can see molar mass on the bottom of that fraction. As molar mass gets bigger, as the mass of the particle gets bigger, gets heavier, that means the speed is going to get slower and slower. All right, so this actually gives you an actual speed, not just how much faster it's going than some other particle. It's actually giving you the speed of the particle. So where u is speed in meters per second, m over s. Okay, average speed of some common gas molecules ranges between about 300 and 3,000 meters per second at 25 degrees centigrade, which is room temperature. So what that is it's showing a graph. Remember we said not all gas particles of a particular type of gas are going to be moving at exactly the same speed. Some are a little bit slower, some are a little bit faster. So what each of these lines is showing for particular gas particles is how fast they're going on average. It's giving you a range. So look at oxygen. Oxygen has an atomic mass or a molar mass, either one, of 32. Okay, so it has a certain average speed, and if you look down below, it looks like it's about 4 times 10 to the second, right? I'm just kind of guessing that based on the horizontal axis down below. I'm guessing oxygen is about 4 times 10 to the second. Now nitrogen has a atomic mass of 28. It's a little bit lighter than oxygen, so you can see it's moving a little bit faster. Its average speed is a little bit to the right. It's a little bit faster. H2O has an atomic mass of 18. So these are all things you can compute from the periodic table. I'm leaving off the decimal point part of it, but it's about 18. So that's much lighter than nitrogen or oxygen, and so you can see water molecules move faster. As you go further to the right, helium has an atomic mass of 4. You can get that off the periodic table. So you can see that its average speed of molecules is moving much faster than oxygen, nitrogen, or water. And finally, hydrogen is the lightest of all. It has an atomic mass of 2. And so you can see its average is way over to the right. It's moving much faster than the other 4 particles are. So air consists of N2 and O2 molecules, which have about the same mass and speed. The graph to the right shows the fraction of common gas molecules at various speeds. Okay, effusion and diffusion. Diffusion is the random movement of gas particles in an open space. So if inside that container on the left you had a little packet of gas particles and you just opened it up and let them fly around freely, they would move in all directions at a certain rate, at a certain speed. That's called diffusion. Effusion is the movement of particles through a small hole, as you see on the container over on the right. Effusion is a laboratory process that allows the speed of gas particles to be measured because it focuses them into a known space. So, in other words, you want to measure how fast those particles are moving, and if they're moving in all different directions, you can't really do that. But if you just want to measure how many go through that one little hole there in that center barrier where the arrow is showing, then you can then extrapolate that. That means you can expand that, whatever that rate is, to an entire area, an entire sphere, and figure out how fast they would be moving in all directions. So you use effusion in the laboratory to figure out how fast the particles spread out. Mean free path is the average distance a gas particle travels before colliding with another particle. So if particles are under high pressure or very low volume, they're going to bang into each other a lot faster than if they're spread out in a larger volume at very low pressures. Okay, ideal gas behavior does not perfectly exist in the real world. Ideal gas particles do not interfere with one another. They move freely. Gases behave most like ideal gases when the temperature is high. This is because the particles have enough kinetic energy to avoid being attracted to other particles. So that goes back to the very first concept we talked about. A gas exists when it has enough kinetic energy to break away from the attractive forces, the Coulombic forces of other molecules and atoms. So if they're at high temperature, they will do that. They won't tend to stick together. Gases also behave most like ideal gases when the pressure is low. This is because the particles are spaced far enough apart to avoid contacting other particles. Now we know as temperature goes up, pressure will go up. So how do you get both of these things to happen at the same time? By making the container very, very large. So if you have a high temperature to keep them from sticking, and you make the container really large, then the pressure will be low. So you can have a high temperature and a low pressure at the same time if you have a large volume for the container. Van der Waals equation makes correction for the fact that gases under high pressure and low volume, which increases pressure, do not behave like ideal gases. Because if they are under high pressure and a very small volume, they're going to tend to bump into each other. That's going to put them close to each other. They may attract each other. They're definitely going to interfere with each other, though. So the Van der Waals equation is, so you see that. I'm not going to ask you any questions on this, just to understand the concept. You notice what it fundamentally is PV equals nRT. The nRT on the right is just like the ideal gas law. On the left, though, you have a lot of other things mixed in with the PV. So A is a factor that represents the strength of the attraction between the particles that makes a gas behave less ideally. So if the particles want to stick together, they're not going to behave like an ideal gas. They're going to start to behave like a liquid or even a solid if they really want to start to stick together. B is a factor that reduces the volume, which increases the pressure. So those are factors that you would have to be given or calculate in a lab experiment. Anyway, what they will do is they will basically deal with the fact that gases don't always behave as ideal gases, and so it's kind of a correction factor. It's a way to correct the calculation. Anyway, I just want you to understand the concept of what this equation is. You don't have to work any problems with this. In summary, larger values for A or B mean that the gas behaves less like an ideal gas. So if A and B went to 0, you can see, then on the left side you would simply have PV, the normal ideal gas law. As they go above 0, you're going to see you're going to end up with something that's going to change that value. Okay, so that takes care of this. This was a fairly long lecture, but I'm not going to ask you any questions on the assignment for a lot of this, but I did want to go over this material. This was actually going to be 2 different lessons, and I just decided to crowd it into one and give you a very limited number of problems. So this is really all part of Lesson 17. All right, so we will move on to other subjects, to solutions next week, and come to tutoring if you have any questions. And that's it. Have a good day.